So this is an example taken from one of my earlier research works on nickel titanium shape memory archwares used for orthodontic applications. So the nice thing about these wires is that at low temperatures, these wires exhibit a phase that is highly deformable. So you can twist it, turn it, give it any shape. While at high temperatures, typically when these wires come in contact with the body, it undergoes a phase transformation, and together with that is a shape change which is associated. So these wires are actually trained to go to a particular shape at high temperatures, and this is what we call as a training in shape memory alloys. So during the clinical use or clinical treatment, these wires are inserted into the oral cavity from a low temperature state, and when these wires experiences a temperature change, it undergoes a phase transformation and a shape change, as I was telling you earlier. And during this shape change, this wires exert small forces on this misaligned teeth to bring it to a more correct position. And this is how the treatment goes. So typically the treatment time takes from 3 months to few years, depending upon the complexity of the misalignment of your teeth. It is therefore important to control the phase transformation temperature window in these materials, and we tried to look into how fine-tuning the microstructures could control the phase transformation characteristics in these materials. So we tried to simulate the processing of these materials through lab scale deformation process called morphomming. So this is typically carried out in liquid nitrogen atmosphere. It's a very sophisticated process. So the post-morphomed and the post-annealed microstructure brings out significant differences. The same region has been seen under microscope before and after annealing. So what we could see in the post-morphomed or the post-deformed microstructure, there's a significant strain heterogeneity that is seen through dense dislocation blocks or walls. That means a higher dislocation density, which could not be indexed to EBSD, and that is the reason why some of these regions appear black. So we tried to further look into these dislocation structures through transmission electron microscopy, and we found that certain grains had this banded structures of dislocations. So these grains which had these dislocation structures were found to have orientations typically denoted by ND parallel to 111 orientation, so these blue colored grains. And interestingly, upon annealing, fine clustered grains of ND parallel to 110 orientation of these green grains were seen to be evolving in these regions of higher dislocation density. So morphomming without annealing shows no phase transformation. However, slight annealing could bring back the transformation in process seen through this pair of peaks in the calorimetric plot. So the transformation here I'm referring to is the transformation from the high temperature state to the low temperature and the reversal of phase transformation. So again, morphomming without annealing introduces significant strain heterogeneity that is seen through dense dislocation blocks or dense dislocation walls that acts as obstacles for the phase boundaries to transform during the forward and the reverse transformation. The ease of phase transformation actually depends on the extent of annealing, the annealing time and temperature. However, there are other factors too, the mode of deformation, the level of deformation that can also significantly alter the microstructure that in turn can also control the phase transformation characteristics in these materials. So this was work that I carried out during my PhD research, and it was one of the interesting part of my PhD thesis.